So hi guys, and welcome to today's video course. In today's video we're gonna cover pointers in embedded C programming. We'll start first of all by showing how to set up our STM32 makefile project. This project will be used mainly to demonstrate the different concepts that we're gonna learn about pointer in C's across this course. We'll be able to compile this project, load it, and debug it. In terms of theory and concept, we'll start by covering the exact definition of pointers in C. We're gonna see the software aspect as well as the hardware aspect of this definition. And we'll see as well how we can declare and define pointers in C. We'll be able as well to see how we can initialize and assign values to our pointers, as well as how we can distinguish between the different pointers and constant combination, like pointers to const or const pointers or const pointer to const. We will see as well how we can cast our pointers, and finally how we can utilize this UNPTR C type to preserve and cover this portability aspect of pointers across our C code. Now to set up our project and to be able to debug the different examples, use it to demonstrate and show up the concepts that we have learned across this course, we'll need first of all in terms of hardware an STM32L4 Nucleo port. This is the port to be used across this course. However, feel free to utilize any other equivalent STM32 microcontroller. In terms of memory map, most of the STM32 microcontrollers share the same memory map. What will be different mainly will be the size of the flash memories and RAM memories. However, the base addresses of flash or RAM in general are the same across the different STM32 microcontrollers. Now, besides the hardware, you will need set of tools to be able to build your project. We'll need, of course, the compiler as well as set of tools to manipulate the different sources and headers. I have put and centralized all those tools and toolchain as part of this Wadix technology tools GitHub repository, and this is the link to the repository. I'll provide anyhow the slides as part of the YouTube video, and I will provide proper descriptions on how you can check out this repo. Finally, you will need, of course, the project source code itself. This is as well part of our Wadix technology GitHub repository, and this is the link to the project. We'll need now to clone and check out our Wadix tools GitHub repository under C drive. My recommendation is to pick up C drive because it offers short paths to the different tools and applications to be used out of our tools directory. Now, in terms of tooling, our Wadix tools GitHub repository offer quite big number on terms of toolings and applications. Nevertheless, for our makefile based project, we will need mainly the ARM GCC compiler. This is the ARM non-EOB GCC compiler from ARM, and this is targeting mainly the ARM Cortex-M microprocessors family. Our makefile project will be an ARM Cortex-M3 based project. Then we'll need this GNU Win32. This one does contain already our GNU Make Build tool. And finally, we'll need set of tools and applications to be used in combination with our make file. So those applications will be used as part of our makefile rules to create directories, remove directories, copy files, change or modify existing files, and so on. Cgwin64 does provide those set of applications. Example, we can create directory via this mkdir application. We can remove via rm as well as rmdir for directories, and so on. Now we'll need to set up our Windows environment variable path to point to those applications and tools. Hence, the Windows system will be able to recognize the location of those tools and applications once they get invoked via the command line. For that, I have prepared this PowerShell script install environment. Once executed from a PowerShell session, then the Windows environment variables for the current account will be updated to point to our applications and tools needed by our project. If you want to revert back, then you can use this an installation environment PowerShell script. So this to install, and this is to restore back the old paths. To execute those scripts, you need first of all to open a PowerShell session. So like this, as you can see. Then the first thing to be done within the current active PowerShell session is to enable the execution policy. This one enables PowerShell to accept external scripts and execute them. Without running this command, the PowerShell session will block the execution of our PowerShell installation script. Once we executed this set execution policy, we can navigate to our tools directory. Then we initiate the execution of our installation PowerShell script. Once done, the Windows environment variable path will be updated and pointing to our applications. So if we inspect the environment variable of our account, then we go to path. As you can see, the path has been updated to point to our Cgwin64 applications as well as make build tool as well as the ARM GCC compiler. If you want to revert back, then you can just execute the uninstall PowerShell script. Now if we inspect again, as you can see, the previously added tools has been removed. Now I will just execute again this install PowerShell to be able to move forward within our makefile based project. As you can see, this has been added again. Now we can move forward and check out our makefile based project. In terms of definition, a pointer in C is merely a memory address that contains the address of another variable. If we are going to declare and define a pointer within our embedded C source code, the pointer itself will have a location or memory address. This will be the pointer address or location. And this is, as you can see, a valid address value. This address value or memory location will contain another value. And this one is just the address of another variable. So when we are declaring a pointer that is pointing to this var, means the address of our pointer, which is allocated by the linker, will embed the address of this var variable. And of course, the address of this var variable will contain the final value assigned to our var. So from hardware perspective, the pointer is just a way to access the content of this variable using the memory addressing. And with those memory addressing manipulation, we can just assign as many pointers as we want, pointing to the same or to different variables locations. So guys, this is our makefile based project, and this one will be targeting an ARM Cortex-M based microcontroller, and to be more precise, we'll be targeting an STM32 microcontroller. The project will consist of a set of examples, and each of these examples will demonstrate a concept that we have learned across the different slides that we have already checked. Now the first example will be used mainly to demonstrate how we can create a pointer, then initialize it with already an existing variable, and finally we'll see how we can modify the content of the pointer itself. Now, to build the project, you will need to invoke this command. As you can see, here I'm trying to clean up the project itself. The different commands to be used will be part of the documentation of this project. Now, I will build the example. So here I need to specify the example to be built, which is example number 0. Once done, we'll have this build directory created, and we'll have this pre-configured Keil project. This is dedicated for an STM32L4 microcontroller. We'll load the binary into flash memory, then we'll start a debug session. I will jump right away to our example. Now here, this is the variable, and I will try to dump the different variables and pointers within our watch window. Now, the variable itself will have an address, and this address will be located within the RAM area. So this is the memory location of our variable, and this one is initialized to 0, as you can see. We have declared as well a pointer. The pointer itself will have an address, and this is the address of our pointer. So always we need to distinguish between the address of our variables and the address of our pointers. So the pointer itself will have an address. And here we'll try basically to modify the content of our pointer. But before executing this line, we need actually to see or focus on this initialization. Here we are initializing our pointer using the address of our variable. This means that we are updating the content or the memory location of our pointer with the variable address itself, as you can see. So this is the address of the pointer, and the address of the variable will go right away to the pointer location. With that way, the pointer will be able to point directly to the variable. And hence, we can update the content of this variable through the pointer. So here we'll have two ways to update this variable. Either via direct access, so we invoke the variable here and then we try to update it, or via the pointer itself. Now let's try to update it. So this is the pointer, this is the address of the variable, and this is the content of the variable. Let's maximize the window. Here we go. So we were able to update the content of our variable through the pointer itself. And this is the magic behind the pointer, is the possibility to update the variable without having a direct access to the variable itself. So this is kind of a way to access remotely the content of the different variables. Now, from software and programming perspective, this is the way basically to declare a pointer within our C code. You will need first of all to specify the name of the pointer, then utilize this star qualifier, and finally we need to specify the type of the variable that our pointer is pointing to. This means this is the type of the variable which its address is contained within the pointer location. You can declare, as stated here, the pointer this way, and you leave it without initialization. But this is always kind of risky. One habit, if you don't have in mind any initial value to be assigned to the pointer, is to assign it by default to null. So this is what is called zero pointer, and in general it is pointing to address 0. So in our case, this pointer would be pointing basically to a variable located in address 0. And hence, whenever we try to access the content of this variable via pointer, we'll end up by accessing the address 0. Another way is that we declare a variable, as you can see here, or structure or whatsoever, and then you pass the address of the variable or the structure to the created pointer. In this case, the pointer location will contain the address of this variable, and hence to access the content of our variable, we'll just need to utilize the pointer to access the address of this variable that will contain this value. And here we are safely initializing our pointer. Another way is just we use another pointer to initialize another one. In this case, I have two pointers, pointer 0 and pointer 1. And here I am assigning pointer 1 to pointer 0. In reality, this means that both pointers 0 and pointer 1 will be pointing both to the same location. Here we are trying to illustrate the mapping between the software manipulation of pointers and what is happening in reality at hardware level. In this case, we have declared a variable which gets initialized by this value 10. At hardware level, this variable will get in reality assigned a memory location. So this will be the address of our variable, And by the way, to obtain the address of our variable, we can utilize basically this syntax. And this value 10 will be stored within this address. In next line, I have created this pointer. Then I made the pointer pointing to this variable. Means I utilized this variable to initialize the pointer. To do so, I will need to pass the address of the variable to our pointer. So from C perspective, this is considered by itself as another type of pointers. Now at hardware level, what is happening is that this address used for our variable will be stored within the pointer location. So the moment I have created this pointer, we'll have an address or memory location allocated to this pointer. And here, when I am initializing the pointer with our variable address, I am actually storing the address of the variable within the memory location of the pointer. With that way, the pointer can access the content of this variable via the variable address. So here I am just creating kind of link between the pointer address and the variable address. Here we are having another more sophisticated use case where we're gonna use two variables to initialize two pointers, and then we'll show up how we can utilize one pointer to initialize another. So as you can see, I have declared two variables, variable 0 and variable 1, and for each of those variables I have initialized them with different value. Now at hardware level, what will happen is that we'll have a memory location assigned to each of those variables. So this will be the memory location assigned to our variable number 0, and this will be the memory location or address assigned to our variable number 1. And the content of the variable 0 address will be here, as you can see. And for the variable number 1, the address or memory location will contain this value. Now in the next lines, I have created two pointers, pointer number 0 and pointer number 1. I have initialized the pointer number 0 with the address of our variable number 0, and the same thing for our pointer number 1. In reality, this means that for pointer number 0, which will be allocated as well a memory address, this one will be initialized with the address of our variable 0. So the memory location or our pointer address will contain the address of variable number 0. Same thing for our pointer number 1. So the pointer number 1 memory location or address will contain the address of our variable number 1. Now here I am going to initialize our pointer number 0 with the value of another pointer. Here this means at hardware level that the pointer number 0 will contain the address of the variable number 1. So the address of our pointer will contain and will be updated with the address of the variable number 1 instead of the variable number 0. With this way, the pointer number 0 will be pointing to the same variable as pointer number 1. Hence, we'll have what is called pointers alias, means having two pointers pointing to the same location. So guys, in this example, we'll see how pointers assignment will lead of having different access types to the same memory location. First of all, I have declared those two global variables. The first one of type uint8, the second one of type uint32. In 32 bits basis system, the first variable will occupy single byte, and within the same system, the second variable will occupy 4 bytes. Then I have defined those two pointers. The first one is pointing to a variable of type uint8, and the second one is pointing to a variable of type uint32. Then I have utilized the addresses of previously defined variables to initialize our pointers. And as you can see, the type of the variable pointed by each pointer will be matching basically the type of the variable used to initialize our pointers. Then I will have this global variable to be used to read out the content of the variable pointed by our pointer. Now within the example function, I will perform this explicit assignment by using this second pointer to update our first pointer. What we need to keep in mind is that this pointer can be used to perform 8 bits access to the content of the pointed variable, and the second one will be used or allow accessing the content of the pointed variable using 32 bits based access. When we are doing this assignment, then the value of this pointer will be the same as this one. Means we'll end up by having two pointers pointing to the same variable. In this case, both pointers will be pointing to this variable. Still though, to access this variable via 32 bits access or transaction, then we'll need to utilize this pointer. This one can enable only 8 bits access. Now, if we try to access this variable using this pointer, then we should get only the first byte, simply because this is 8 bits based pointer. So although both pointers are pointing to the same variable, but this one, as stated, will be used for 32 bits access, and this one will be used for 8 bits access. I'm gonna load now the example into our STM32 microcontroller. Then we'll start a debug session. Here I have dumped most of the variables, content, their addresses, as well as the pointers within this example. Now each variable will be allocated a memory location or address, and this is the way basically to obtain the address of different variables. The addresses of different variables will be used to initialize the values of our pointers. So the address of our variable 0 is used to initialize our uint8 based pointer, and the address of variable 1 is used to initialize the value of pointer 1 or uint32 bits based pointer. This is the content of our variable 0, and this is the content of our variable 1. If we try to access the content of those variables via those pointers, we'll get the same values. So really, as you can see, pointers are just two ways to access the different memory locations, but with different methodologies or ways. So we are not doing explicit access like this. We are just using different memory addresses or space to access the content of those variables in an indirect way. When we are going to do pointers assignments, then we are updating the value of this pointer. Updating the value means this pointer will be pointing to the same memory location as this one. So we'll have two pointers pointing to the same variable, which is this one. So this address is the value of this pointer uint8 and this pointer uint32. However, what will be the difference is that if we're gonna use this pointer to access the content of this variable, then we're gonna perform 8 bits access. Hence, we'll be able only to read the first byte. If we're gonna use this pointer, then we're gonna use 32 bits access. Hence, we'll be able to read out the full value of our variable. Now let's try to use the uint8 based pointer to read out our variable. Now here we go. The obtained value is only the first byte. So, although we can define as many pointers as we want and have them all pointing to the same memory location, but the type qualifier of each pointer will have big impact in terms of access size. Hence, we can perform 8 bits access, 16 bits access, 32 bits access to the same memory location using different pointers. We'll start now by listing the different combinations between pointers and const type qualifier, like pointer to const, or const pointer, or const pointer to const. We'll start first of all by pointer to const. Here we can declare a pointer and the type of the variable that the pointer is pointing to will be const. Hence, the pointer itself we can update, but the variable that the pointer is pointing to cannot be updated. Hence, if we try to use the pointer to update or modify the variable, then we'll get a compile time error. In this example, I have created a variable of type integer. Then I used the address of this variable to initialize this pointer. This one has a type qualifier const integer, means it is pointing to a variable that will have a const integer type. Now, if we try to access the content of the variable through the pointer, as you can see, and we try to update it, then the compiler will generate a compile time error. One side note concerning this use case is that it is recommended that the type of the variable used to initialize our pointer have the same type qualifier as the pointer. Here in our case, our pointer is pointing to a variable of type const integer. However, the variable used to initialize our pointer has type integer only. So we are having kind of mismatch between the type qualifier used for our pointer and the one used for our variable. But since the mismatch is only for this extra const type qualifier, then our compiler will accept it. In some cases, we may have some warning, but in general, we can compile this code. However, from readability perspective, and to avoid as well any kind of warning, it is recommended to keep the same type qualifier between the pointer and the variable used to initialize our pointer. In the second use case, I have tackled this problem or mismatch in terms of type qualifier between the pointer and the variable. And hence, as you can see, the variable used to initialize our pointer will have the same const type qualifier as our pointer. And this is the recommended use case. But as first use case, we cannot modify or update the content of this variable through our pointer. The compiler will generate a compile time error because we are trying to update and modify a const variable. So the behavior will be the same as accessing the variable itself. So if we try to update this variable directly, we'll get a compile time error because we are trying to update a const variable. And here, if we try to update the content of this variable through the pointer, using basically this syntax, then we'll get as well a compile time error because the compiler sees that the pointer should point to a variable of type const integer, and hence we cannot update this variable pointed by our pointer via the pointer itself. This is not allowed. Here in the first use case, although we cannot update the variable via the pointer because we have this const type qualifier associated with the type of variables pointed by our pointer. However, the variable itself, which is used to initialize our pointer, can be updated. For a basic reason is that we don't have the const type qualifier in this case. So guys, in this example, I have declared this pointer pointing basically to an integer variable that is marked with the const type qualifier. This means simply that if we try to access the variable pointed by this pointer via the pointer itself, then the compiler will throw a compile time error. In this example, I have initialized this pointer to const using basically this pre-configured or defined variable. This variable itself is not marked as const. Hence, we can update it directly within our source code. However, I use the address of this variable to initialize our pointer to const. Now, if I try to access the variable content via the pointer, not directly, then the compiler will throw a compile time error. So let's try it. And here we go. the compiler will throw an error regarding an assignment of read-only location, which is this one. This is simply because the type of the variable that this pointer is pointing to has this const type qualifier. Nevertheless, if we try to update the variable itself, not through the pointer, but by a direct access, then the compiler should not throw any kind of error. And here we go. Simply because we don't have this const type qualifier assigned or associated with our variable declaration. Now the second use case of this const and pointers combination will be what is called const pointer. In this case, the const part will be our pointer itself, and the variable that we are pointing to will not be a const. Hence, our pointer cannot be updated. However, the variable that we are pointing to can be updated. Now, as first example, I have created this integer variable. Then in the next line, I have created a const pointer to an integer. Then initialized this pointer using the address of our previously created variable. And here I am trying to update the variable that is pointed by our pointer. Here we can actually update this variable because the type of the variable that our pointer is pointing to is not a const. Hence, it is updatable. So this line will not throw an error. In the second use case, I have defined two pointers, pointer 0 and pointer 1. Those two pointers are initialized using the addresses of those two integer variables, variable 0 and variable 1. Both pointers are const, and both are pointing to a non-const integers. So theoretically, I cannot update those pointers, but I can update the variables pointed by those two pointers. In this last line, I am trying to update my pointer number 0 using the pointer number 1. This operation will not be allowed, simply because our pointer number 0 is const. Hence, we cannot update it or modify it. So the address of our pointer number 0 cannot be updated. And if we try so, then the compiler will throw a compile time error. Now, in this example, I have defined and declared two const pointers. So the pointer itself, in this case, is of type qualifier const. However, the variable that the pointer is pointing to is not having this const type qualifier. This means simply that we cannot update or modify the pointer itself. However, we can update the content of the variable that will be accessed via the pointer itself. Now, let's try basically to update this const pointer using another const pointer. And here we go. The compiler will throw a compile time error, simply because we are trying to update a const pointer, and this is not allowed. However, if we try to update the variable that is pointed by this pointer, then we'll not have any kind of problems, simply because this is not a pointer to const. The const type qualifier is only associated with the pointer itself, not with the variable pointed by this pointer. So we try to update basically our variable here through the pointer. And here we go. We don't have any kind of problem here. We don't have this const type qualifier associated with our pointed variable. This is only associated with our pointer. Now the final use case will be the extreme one, where we will have a const pointer to a const. In this case, the pointer itself will be const, and the type of the variable we are pointing to will be const as well. Hence, we cannot update neither the pointer, neither the variable we are pointing to. Here I have defined two variables, variable 0 and variable 1 of type integer, and have initialized those variables as you can see. Then I have created my first pointer, pointer number 0. This one is a const pointer and it is pointing to a const integer. And I have initialized my pointer initially with the address of variable 0. It is true that our pointer is const, but during the creation of the pointer, it is allowed to assign to it an initial value. However, later on, we cannot update the pointer. Then I have created another pointer, which is pointer number 1, and this one is a normal pointer, so it is not a const pointer, and it is pointing as well to a normal variable of type integer, not a const variable. Then I utilized the address of the variable 1 to initialize our pointer. If I try to access the variable content through this pointer number 0, means trying to update the variable number 0 through the pointer, then the compiler will throw a compile time error. Because when I have created this pointer, I have specified that the type of the variable we are pointing to has the const type qualifier. Hence, trying to update this variable via the pointer using this syntax will throw a compile time error. Nevertheless, if we try to update the variable directly and we bypass the pointer syntax, then yes, we can update it because we don't have the const type qualifier with or associated with our variable. And here I am trying to update the pointer itself using the pointer number 1. Means I am trying to update the address of my pointer number 0 and store there the address of the variable number 1, so that pointer 0 and point 1 will be pointing to the same variable. However, and because my pointer number 0 has this const type qualifier, then this operation will be not allowed and the compiler will throw a compile time error. In this example, I went right away to the extreme use case where I have declared a const pointer to a const integer variable. So the pointer itself will be const, and the variable pointed by the pointer will be const as well. Hence, we cannot modify neither the pointer neither the variable pointed by this pointer. So if I try to access the content of the variable via the pointer using this syntax, then we should have or get a compile time error. And here we go. The compiler will throw this assignment of read-only location error, simply because the variable pointed by this pointer is marked with the const type qualifier, and hence if we try to access the variable via the pointer like here, then we'll get this compile time error. Now if we try to modify the pointer itself using the address of this variable, then we should get as well a compile time error. Again, we'll have the same error, simply because the pointer itself is marked as well with this const type qualifier. Pointers casting consists mainly of converting a pointer from one type to another. In this example, I have created a pointer out of this memory address, and this pointer will be 32-bit based pointer. Means the variable that this pointer is pointing to will be 32-bit size. In this line, I have casted and converted this pointer to be 8 bits pointer instead of 32 bits. To do so, we need to specify explicitly the casting type up front of our pointer, and hence we can use this full syntax to access again our memory address. Of course, to access the content of this address, we need to specify this start here. The main difference between using this pointer directly to access this address or using this casted version of the pointer is that here the access will be 32-bit spaced access, simply because our pointer is 32-bit spaced one. The casted pointer, on the other hand, is 8 bits based pointer. Hence, the access will be 8 bits instead of 32 bits. We can as well create an 8 bits pointer out of the casted one. And hence we can initialize this pointer with the casted pointer. In general, the pointer's casting has some pros and cons. It depends mainly from your source code and software. However, when you are going to utilize the pointer's casting, you need to make sure that you restrict yourself to your hardware limitation, as well as you respect basically some C coding style. Example, you need to make sure that you don't violate the address alignment restriction within your hardware. So some hardware, they may accept aligned access only, and some hardware, they may accept aligned and unaligned access as well. If we don't take care of the alignment of our casted pointers, then we may find out ourselves making implicit unaligned access in a hardware that doesn't support this unaligned access. Here we have the 32-bit spaced pointer. Hence, if we're going to use this pointer to access this memory address, then this access will be 32 bits. And this is the 32 bits aligned address. So the access is aligned. This is not an issue. Here, the access will be 8 bits based access because this is an 8 bits pointer. If we initialize this pointer with different address, which is 1 byte aligned, then we cast this guy to be 32 bits, and we utilize this 32 bits pointer to access the same address, then we'll end up by performing a 32 bits access to a byte aligned address, and this is considered unaligned access. For hardware that doesn't support this unaligned access, we'll end up by having a fault. Also, you need to respect certain C rules restrictions. Examples when it's come to the types of the pointers. We may have an integer based pointer, and then through casting we may create another pointer of type float, and then we'll end up by having two pointers if this is get initialized with the same pointer but getting casted. Then we'll end up by having two pointers pointing to the same location, but each pointer will have a different type. This of course will create some issues when it comes to the precision of the data reading from this memory address. In general, pointers casting will lead to what is called memory alias, which means having two pointers or more pointing to the same memory location. And then we end up to some problems if we are having different types for each of those pointers. Also, we may have problems with alignments and so on. Although the pointer casting is a strong feature within C and C++, but we need to make sure that we utilize it in proper way. In this use case, I have created and defined a pointer to a variable type UN32. Then I have used the 32 bits variable address to initialize my pointer. Means this pointer will be pointing now to this variable, and hence I can utilize this pointer to make indirect access to the content of this variable. So I can read out this value via the pointer itself. Now the thing is, this is a 32 bits based pointer. Means if I am gonna use this pointer for indirect access to the content of this variable, then we'll be performing a 32 bits access. And hence, if I perform this 32 bits access, I will be able to read out the full value. However, if I want to read only the first byte of this variable, then instead of doing some shift operation or creating basically some intermediate variables here or whatsoever, I can just create another 8 bits based variable, then update it with the value of this pointer. So we'll end up by having two pointers pointing to the same variables. One to be used for 32 bits access, and the second one to be used for 8 bits access. However, to properly create the second pointer, we need to perform pointers casting. In such a way, we are sure that the second pointer is 8 bits based pointer. I will create now the second pointer here, and I will name it like this. This new pointer will be initialized using the same EN32 basic pointer. However, the type of this pointer is different from this one. So to have proper assignment, I need to enforce the casting. So here I am casting this 32 bits basic pointer to 8 bits basic one. And then I will perform a second access basically to the same memory location or variable, but this time I'm gonna use this new created 8 bits basic pointer. I will recompile the code. Then I will try to load it via Keil project. Now the first time I perform a read of the content of this variable using this 32 bits basic pointer, I will perform actually 32 bits access. So if I dump now the content of this temporary variable, we're gonna see basically the full value stored here. Now I will create this second pointer, then perform another access to the same variable, but this time via this 8 bits basic pointer. This assignment means we'll have both pointers pointing to the same variable or memory location. And here we go. Now our temporary variable has been updated and contains only the first byte of this variable, simply because we have used this 8 bits basic pointer instead of 32 bits to access this variable. Hence, we'll end up by performing 8 bits access to the content of this variable instead of 32 bits access. Now in this example, we're gonna see how pointers casting can lead to what is called pointers alias, and how this pointer alias can introduce certain risks in terms of memory alignment. So first of all, I have declared this pointer, which is pointing to a variable of type uint8. Then I have utilized this previously declared uint8 variable to initialize our pointer. In the next line, I have declared a pointer to a variable of type uint32, and this pointer is initialized with null. Now, the alignment of the variable that each pointer is pointing to depends actually from the capabilities of your platform. Now, for 8 bits or a byte basic variables, the alignment of course will be 1 byte. However, for 32 bits variables, the alignment in general depends from the capabilities of your hardware. So if unaligned access is supported, then the 32 bits variables can be allocated in 1 byte, 2 bytes, or 4 bytes basic memory alignment. However, if unaligned access is not supported on our hardware, then we must allocate 4 bytes basic memory alignment to our 32 bits variable. And of course, any attempt to do unaligned access will lead basically to a fault. Unaligned access, something like performing 32 bits access to a byte or 2 bytes based memory aligned address. Here I have declared this variable. I will utilize it mainly to read out the content of the variable pointed by our 32 bits based pointer. Within the example function, I will try to assign this 8 bits based pointer to this 32 bits based pointer. The assignment itself is not wrong, so we can assign pointer to pointer. There is absolutely no problem there. The issue there is that the type of this pointer is 8 bits and this one is 32 bits. As a result, this 32 bits based pointer will be pointing to a variable of type uint8. This one will be byte aligned. If we try to access this variable through this 32 bits based pointer, then the hardware will initiate a 32 bits based access to 1 byte address aligned. This is exactly an aligned access. And for a hardware that doesn't support this unaligned access, we'll end up by having a fault. Hence, this pointer alia, which consists of having those two pointers pointing to the same location, can introduce certain risk. Because here we think that we can access basically this variable without any problem. However, we overlook that the second pointer pointing to the same location is 32 bits based pointer, and hence this one will enable this unaligned access by performing 32-bit access to byte based aligned address. So always adjust basically your pointers assignment, casting, and alias to your hardware capabilities. Another valid use case within embedded devices is having the ability to read memory locations via software. This can be achieved via pointers utilization. So here we need to define basically the address that we want to access. This can be stored within a global variable. Then out of this address, we'll need to create a C-based pointer. To do so, we'll need to cast this address to this uint32 based pointer. And then we assign this to this locally created pointer. The end result is that this pointer will be pointing to a variable that is having this address. And accessing the content of the variables pointed by these pointers is the same as accessing this address, simply because the variable pointed by this pointer will have this address. And hence, if we try to read out the content of this pointer, we'll end up by reading out this memory location. So we'll try to dump the content of this memory location via memory browser. So this is the content, as you can see, and if we try to dump the content of our temporary variable, then we run, and here we go. So this is matching. So with this tip, you can basically dump any memory location within your embedded device via software. In C programming language, we have the support of this uintptr _t type. This one is used mainly to hold the pointer numeric value. The pointer numeric value is the address of the variable that is contained within the pointer address itself. In this example, the pointer value will be the address of our variable x. This uintptr type is part of the stdint.h C header. This one, as stated, can be used to store and hold the value of the pointer itself. In this example, I have created this address of type uintptr_t. Then initialized this numeric value or address with this pointer value. This uintptr_t type offers an abstracted way to hold the value of the different pointers. Hence, the C standard or the C header will make sure that this type is large enough to hold the current platform pointer size, because we don't have only single 32-bit system. We may have 64-bit space system or 16 bits and so on. Now, to abstract the maximum size of the pointer to be stored, we can just utilize this type. And hence, we are making sure that this one is large enough and matching our platform requirements and limitations. Hence, it will match the maximum supported pointer size within the current platform. So the user doesn't need to take care of the exact type to be used here to be able to store properly the pointer value. We should just enough invoke this new type and then do the assignment of our pointer value to this newly created address. So it makes the code platform independent, means we don't need to take care if our platform is 16 bits, 32 bits, or 64 bits. This one will abstract basically this information. And of course, out of this address variable, we can later on recreate our pointer easily. So we are doing a pointer casting here to create our pointer, and this one will be exactly the same as here.